Welcome to F453 by Jam. Today we are covering Chapter 2, the function and purpose of translators. The contents of this video are programming background, translators, the translation process, immediate code and virtual machines, and library routines. Let's get straight into it. In the early days of programmers, programs were made in binary. First generation programming. Instructions are made of two parts: OP code, the binary instruction, for example an addition instruction, and operand, the part of the data to be operated, usually some value or address stored in memory. Programmers wrote in binary because this is what the machine understands. It is machine code. Obviously, this isn't the most efficient method. It's very time demanding, limited, repetitive, and error handling is abysmal. Don't worry, for humans developed better alternatives. Enter the translator. A translator is a software used to translate code. A programming language is pretty much defined by its translator. A translator's main job is to translate code written by humans into code written by the machine. It also provides error handling, as no programmer is perfect. There are three kinds of translator you need to learn, listed in the table. Second generation programming. Low-level language, or assembly language, was developed. Mnemonics are short keywords, such as add, used to refer to one OP code. Labels, such as num1, are used to refer to memory addresses. Assembly language is easier to understand and debug. Assembly language is still useful today. Your washing machine contains a simple program stored on a small memory chip. It needs direct access to memory locations in a small size. Assembly language has a one-to-one relationship with machine code. For every OP code, there is a mnemonic. For every label, there is an operand. It is translated using an assembler, a small piece of software specific to the make of the machine. Mnemonics are stored in a lookup table, and the memory address is allocated to each label. Third generation programming. Nowadays, we are mostly concerned with high-level languages. Fortran is the first of these, developed at IBM during the 1950s. Developed later are C++, Python, Java, PHP, SQL, etc. Code developed in high-level languages is called source code. It can be saved in a text-based format and translated when it needs to be. Let's talk about the advantages. For a start, it's closer to human language, and this makes it easier for us to understand. It lowers the boundary for understanding of computers for potential coders. Keywords have a one-to-many relationship with machine code. This reduces repetition and makes source code smaller. It improves portability, as we'll see later. It can't be translated using an assembler. Why? Because its keywords are one-to-many. An assembler operates on a one-to-one format. Instead, we translate source code using a compiler or an interpreter. So, what is a compiler, you may ask? What's an interpreter? Well, both are translators used to translate source code. Both report errors in the code. There are many more differences than similarities. I'll be using animations to highlight them more clearly. I'm moving on to the next slide now. Here's how a compiler works. The source code is translated as a unit, reporting errors along the way. It can now be ported to different machines. The compiler is not required. It's fast. This is because everything has already been translated. Intellectual property is protected as there is no need to distribute the original code. However, more memory is required at any one time because the program runs as a unit. Runtime errors resulting from the executable itself will cause the computer to crash. Now let's move on to the interpreter. The source code is translated line by line, executing each one as it goes. The computer requires the interpreter and the original source code at runtime, else it won't know what to do. This also means weaker intellectual property. Because it must constantly be translated, the programmer will run slower. Less RAM is required because you are only handling the current line. Errors are caught and translator diagnostics can be made. This is useful when debugging. The translation process. Now we know what compilers and interpreters are, we should find out how they work. Let's look at the stages of translation, sometimes called the compilation process. The process is broken into 3 stages: lexical analysis, then syntax analysis, then code generation and optimization. Each stage is a pass of the code, where parsing means to analyze. Lexical analysis is the first stage of compilation. The translator takes a copy of the source code and manipulates it. The first thing it does is to remove comments and whitespace. The source code is replaced with binary tokens, and during this process, some simple errors can be found. Continuing on, literals, variables, and keywords are all tokenized. Each token is stored in some kind of table. Note that the symbol table has to be created at this stage, since we don't know what the variables are yet. Lexical analysis is the slowest phase of compilation because it has to handle the original source code. The second stage is syntax analysis. Backus Neuroform, or BNF, defines the rules of a programming language. If the source code breaks these rules, a syntax error is reported and the translation process is terminated. Logic errors and runtime errors aren't captured at this stage. The syntax analyzer verifies variables and knows information about it. This information is updated to the symbol table. The final stage is code generation and optimization. The source code is completely binary now, and all of the tables are ready. Intermediate code is produced. Optimization removes redundant or unused parts of code. It can favor speed or memory. It is at this stage that the code can be compiled as a unit into object code or interpreted by a virtual machine. What's the virtual machine, I hear? Well, first we must know what intermediate code is. Intermediate code is partially translated code. It's been analyzed and is free of syntax errors, although runtime errors and logical errors may still be present. Since it's all binary now, it doesn't matter what language it was originally made in. It's interpreted line by line by a virtual machine. A virtual machine is an emulator. It allows the code made on one platform to run on another. Intermediate code is not machine-specific and needs further translation. It is the purpose of a virtual machine to carry out this translation. An example to remember is the Java virtual machine. Intermediate code improves portability between machines and allows for multi-platform development. Virtual machines can catch runtime errors so that the program doesn't crash. Can you think of any disadvantages of intermediate code? If you get stuck, it's good to try and link what you know together. Intermediate code is interpreted, meaning an interpreter is used to run it. This makes it slower than object code. Library routines. Lastly, we will cover library routines. You may have heard of library routines before. Windows uses library routines in the form of DLLs. Library routines, such as DLLs, are commonly used modules written for a specific purpose. It's already written, so the programmer doesn't have to waste time writing it. Library routines are stored on the OS. They are utility software. Since it can be used for multiple programs, it saves memory. The only problem is that library routines are updated with the operating system, and you'll have to update your program with them. There are 2 library routines you'll need to know. The linker links code to relevant places, and the loader loads all modules the program requires into memory. Linker tells where to go, loader loads what to do. That's all my slides. Thank you for watching. Strike that like button and subscribe for more F453 related content.